Welcome to the course on modern digital communication techniques. This particular course is offered as a 4-credit course at IIT Kharagpur, and this is usually the first course for the master's program in the first semester. Generally, this is taken by the master students as well as the UG students who take it as elective. It is also taken by research scholars as well as MS by research. This particular program, the particular course works as the foundation course on digital communications for those who have done an undergraduate course on digital communications. Yet the way this particular course is structured for this NPTEL, it would highly suit UG students who would be taking digital communications for the first time as well. In this particular course, what we will be covering is the design principles. The reason being that communications, as you all know, is one of the basic necessities of life. Everything is based on communication. The survival is based on communication. Our entire human system has a whole network of communications which send signals from various parts of the body. As a society, we communicate with each other. So just imagine living for one day without any communication tools or aids at your help. Life would be very tough. Today, where we stand, communication technology has evolved tremendously, and a huge amount of theory has been developed, especially over the last few decades. In this particular course, we will take a look at the details of engineering principles, the theories and fundamentals based on which one should be able to design a futuristic communication system. Accordingly, we have set the objective of this course is to present the engineering principles and design and theories and practice which are fundamental to the successful design of a digital communication system. So, this will be underlining the way we run this particular course. The course will delve into the design principles of a transmitter. So, how you design a transmitter, how you design a receiver so as to establish a reliable communication link. This is very, very important. You can establish a communication link, but if it is full of errors, then there is hardly any meaning behind it. So, one should be able to communicate across from one point to another with as a minimum amount of error as possible, which is one of the objective of designing a communication link. Moving down further, this course aims at enabling the participant to establish an unambiguous mathematical statement describing every step of transmitting and receiving a signal through a communication link. Now, this is very, very important, because if we are able to establish the mathematical notation which describes the signal that goes out from the modem, then we are able to characterize the signal, we are able to study its properties, and we are able to specify in an unambiguous manner to the designer or to the implementer of our design what exactly he needs to take as input and what exactly he needs to give as output. We will see slowly through the various stages why we need such a clear-cut statement. Another very important part of this course is to expose the details of noise. Usually, we have a common statement that if you do not have noise, then communication engineers are out of business. So, basically noise is one which is critical and which is a challenge which the designer generally overcomes. So, in the course on digital communications, noise would be our fundamental challenge, and the way we design our communication system would be to counter noise and design a reliable communication link. We will see more effects further down. So, we will see how it is modeled. Now, why we talk about modeling? Because we are talking about unambiguous mathematical statements. So, if we are talking about unambiguous mathematical statements, we need to model a physical phenomena. Once you model a physical phenomena, you can fit into the mathematical statement of the transmitted signal, and hence you can construct the received signal. Now, once you have a mathematical statement of the received signal, then you can look into it and understand the distortions that have happened, the errors, the probable errors that it can lead to, and therefore, you can design all possible functions, mathematical functions which would help it to recover the errors or overcome the effect of noise. So, that is why we talk about these mathematical statements and models of noise, and they all go hand in hand. So, this is the core of the course on which it will be built. This will be the philosophy of the course on the way how we run this particular subject. Well, it will cover methods for performance analysis. So, since you have designed a system, you need to now analyze its performance. So, we will be giving you tools how to analyze the performance, analytical techniques as well as simulation methods. And through the use of fundamental knowledge developed in the related areas of signal processing. Now, we are talking about communications. So, communication is basically application of signal processing. So, one needs to be aware of signal processing, and through signal processing we will be designing a digital communication system. So, when we talk about a digital communication system, we are essentially talking about signal processing. That is one of the important tenets of digital communications. And it will also encompass the fundamental aspects of estimation detection theory. Now, estimation detection theory is essential for the receiver. Now, why is it so is clearly available in the next few words. For designing of a complete receiver, when we mean a complete receiver, we talk of synchronization, we talk of channel estimation, channel equalization, etc. Synchronization is all about acquiring the carrier frequency, and equalization is about estimating the channel and then equalizing it so that you can detect the transmitted signals. So, you can clearly see or hear the words I have used estimate and detect. Now, these go hand in hand in the domain of communication engineering. So, we need some basics of estimation detection theory which we will provide so that it helps us in creating a framework which we will be using in designing synchronization, channel estimation and receiver algorithms, so that we are finally able to build a complete receiver. At the end of the course, our aim is that the participant is equipped with methods for a systematic representation, analysis and design of a digital communication system. Now, this is the aim. So, towards the end of the course, one should ask himself or herself that if one is able to represent the communication system, if one is able to analyze the performance, and if there are issues, then one should be able to design solutions to the problems that one encounters. So, towards the end of the course, you should be able to do all these three basic requirements, which is a bit abstract in nature, but applies in general to design of communication systems. This is the typical orientation, or this is the flow of the course. The first week we'll do an introduction to communication systems, then we'll talk about source coding, then we'll go into characterization of communications and signals, communication signals and systems, then we'll go into signal space representation, followed by representation of memoryless modulation methods, then nonlinear modulation methods, followed by optimal receivers, then receivers for non-ideal channel. I mean, when we say optimal receivers, it's the additive white Gaussian noise channel when we say AWGN. Then we'll talk about probability of error for different modulation techniques. Now, this is where we are talking about the performance analysis. This is where we are talking about performance analysis. This is where we are talking about signal processing. Then we'll talk about fundamentals of estimation and detection theory, which we'll be using in week 11, where we do carrier phase and symbol timing synchronization, and also we'll be using it in the channel estimation equalization as we do in the week 12 of this particular course. The suggested readings are the digital communication book by John Prokes, then digital communication by Bernard Sklar, communications by Robert Gallagher. We'll be following mainly this number 1 in this particular course. This is a very easy reading book, and we'll follow parts of this book, but the core of the course will be from this particular, will be followed as per this particular book. The one that I generally follow is the 4th edition of the Prokes book. So, it's not available anymore. You now have the 5th edition, but that is also pretty much okay for this particular course. Moving down further, this is the typical representation of a digital communication system. Now, this picture has been taken from the book by Sklar. He has given a very beautiful representation. I have just used it for the sake of demonstration. So, that book is very good to read. Now, this particular diagram, you can see, covers many components. Now, this is the transmitter side, and this is the receiver side. This is the receiver side. So, our aim would be to cover as many of these components as possible. Now, going beyond this particular flow diagram as given in this book, we have another picture which is, this is kind of a bit hand drawn. We will draw this during the course. As you can clearly see here, we have the source coding part, and here you have the baseband signal processing part. Out of this, I have encircled a section which is error correction code. Reason being, we are not going to discuss error correction code in this course, and we will also not talk about the RF section in this particular course. So, this course is about digital signal processing for communications. This is about the baseband signal processing. Further, you can also see from this diagram, I have encircled a particular part which is in green. It might be difficult to read in this particular slide, but we will do it later in the course. We have packet detection, which is a kind of synchronization. We have frame synchronization, we have carrier synchronization, we have clock synchronization, we have channel estimation and equalization. Now, these are unique parts of the receiver which are not required at the transmitter. You require these components only at the receiver side. Now, this makes a communication system very unique, and all these parts require estimation and detection theory. So, this will be one of the important part of the course which we will look at. Rest of it is the reverse processing of the transmitter. This is the reverse processing of the transmitter, this is the reverse processing of the transmitter. So, as we go through the course, our objective would be to slowly take one by one boxes of this particular diagram till the point we start here and we end up here, so that we are able to send something from the source and we are able to detect it at the receiver, design each of the components, measure the performance, and provide an unambiguous statements of the signal representation at each of these interfaces, so that the person designing a particular module can take a specific input and give a specific output. Lastly, I would like to just draw your attention to one particular way of viewing systems, which is called the layered way of viewing a system. That is, if we recall the previous diagram, we could still break it up and see only the source coding part as shown over here. Now, we could say that let us look at this at the transmitter and this as the receiver, and we do not bother about what's in the right hand side of this particular transmitter and receiver. If you look at this, what goes out from this, a sequence of zeros and ones, what goes in over here is a sequence of zeros and ones. The rest of it, if we go back, the rest of it is this part, these parts, rest of it are these parts. So, we have encapsulated the entire thing into something called the binary channel. Similarly, if we move ahead a little bit more and look at the next view, where we talk about the forward error correction code as we have here, and the baseband signal processing or the symbol mapping over here, at different stages we can view the channel in different ways. For example, here if we have a channel border, we would have the channel which takes binary inputs, gives binary outputs. At these points, it takes symbol input, it gives symbol output. At these points, it would take waveform input, waveform output. At these points, it would take electromagnetic signals as input and electromagnetic signals as outputs. So, what I am trying to say here at this point is, we should also learn the way of representing a digital communication system in a layered view, so that we are able to design individual components independent of the components which lie on the left hand side of it or the right hand side of it. More details will come in the course as we go through. Now, this is a 30-hour course, so we have a good amount of exposure to several topics, and I welcome you to this particular subject and hope you will have a good time learning through the basics of digital communications, so that you are finally equipped to design a digital communication system of your own. Thank you.